Thank you.
Dongjie, excuse me for the
You can call me DJ.
DJ works at Tenstorrent on vector unit design. Before that, he worked for the GPU design team at Apple. He received his BS from UIUC, University of Illinois Urbana-Champaign, and an MS from my alma mater, University of Texas at Austin. So he's here to talk a little bit about the vector unit for Tenstorrent. Thanks so much. Go ahead and get started.
Thank you. Before we start, I just want to say I'm a bit nervous about this talk because I'm speaking in front of the people who made the Chipyard and the Boom core, and it felt like a dissertation to me.
Oh, excuse me. You're actually showing the wrong screen. We see the Tenstorrent logo. Tenstorrent.
Yeah, I haven't started.
Oh,
okay. See the screen?
Now, yes, now we can see your slides. Okay, perfect. Thank you. Sorry about that.
All right, let's get started. Hello, my name is Dongjie from Tenstorrent, and I'm excited to share our work on adding RVV support to the Boom processor. This project was initiated by Srikanth, who recognized the potential of Chisel-based Boom design and encouraged me to incorporate support for vector extension. We discovered that Chipyard is an excellent starting point for learning RISC-V ecosystem, building prototypes, and setting up testing environments. We believe it's important to give back to the community by open sourcing our work, which we hope will inspire more people to become part of this thriving ecosystem. In this presentation, I will provide a brief overview of the Boom core, the Chisel language, and the vector unit we implemented. Next, I will guide you through the integration process of incorporating the vector unit into Boom core, highlighting the three major challenges we overcame: Chisel SystemVerilog integration, in-order pipeline in an out-of-order core, and LSU retrofitting. Lastly, I will discuss the debugging harness we developed, which played a crucial role in facilitating our work throughout this project. Many of you in the audience may already be familiar with the Berkeley's out-of-order machine, aka Boom. It's gained quite a bit of attention in recent years due to its innovative approach to processor design. Boom's architecture is highly flexible, allowing for a wide range of configurations to suit different needs. This adaptability extends to the issue width and the number of functional units, making it a versatile solution for various applications. To illustrate this, let me show you an example of a 4-issue large Boom config. In this particular configuration, a vector unit has been added as a new execution unit, complete with its own dedicated issue queue. This addition demonstrates the ease with which new components can be integrated into Boom design, further highlighting its adaptability and potential for expansion. The Boom core is developed using Chisel, a powerful hardware construction language that is built on top of the object-oriented programming language, Scala. Chisel provides a high-level approach to hardware design, making it easier for developers to create complex systems. One of the key advantages of Boom design is its well-defined class hierarchy. This structure streamlines the process of adding new units to the system, as it reduces the overhead typically associated with integrating new components. Moreover, Boom's design is extremely configurable, providing a wide array of customization options. By using config mixins, developers can create a highly tailored CPU core that meets their specific requirements. This includes adjusting the number of int or memory units, modifying the size of physical register files, or enabling certain features, such as the vector extension we integrated. I extracted the vector unit and some accompanying units from a simple in-order core that our team developed. I then integrate these components into Boom as an additional functional unit. The vector unit was implemented following the specification of the RVV version 1.0 standard, which was officially ratified in late 2021. It is designed to support the vector extension with a parameterized VLAN, allowing for greater flexibility and scalability in processing vector operations. To provide a more detailed understanding, let's examine this diagram of the vector unit pipeline. It features several key components: a built-in instruction decoder and the vector register file located in the front end, an agent specially designed for vector load store instructions, and a fully pipelined data path capable of handling operations with the various latency. The vector floating point unit is built using open source hard float arithmetic units, supporting half, single, and double precision floating point operations across all rounding modes. However, due to the time constraints, the vector unit currently doesn't support division and the square root operations, as they don't integrate well with the three-stage pipeline, and may require pipeline blocking. The primary aim of this project is to enable support for vector extension with an out-of-order core while operating under the constraints of limited resource and time. To achieve this goal, integrating Boom with a functional vector unit seems to be the most appropriate strategy. Successfully completing this project involves overcoming three main challenges that arise during the integration process. Integrating a SystemVerilog module into a Chisel-based design, incorporating an in-order pipeline into an out-of-order core, and retrofitting the load store unit. By addressing these challenges, we can successfully integrate the vector extension support into the Boom core. Chisel Black Box offer an exceptional approach to instantiating SystemVerilog-based modules within a Chisel design, allowing for seamless integration of components from different hardware description languages. However, one issue that arises from Chisel's verbose nature is a difficulty in instantiating modules that utilize structs or multidimensional arrays as part of their interface. This can present challenges in maintaining compatibility between the two languages. In order to address this issue, we develop a solution that involves creation of wrapper modules. These modules function to convert the separated signals from the Chisel design into a consolidated packed format. In this instance, one of the RTL signals that our debugging harness reports is the commit signals. However, these commit signals are formed in an array of structs, and their size depends on the number of issues. On the Chisel side, the commit signals are defined as a vector of bundles, while on the SystemVerilog side, they are defined as an array of structs. Our challenge was to enhance the existing black box functionality to support linking these two types of signals and supports the various configurations. To overcome this challenge, I utilized two wrapper modules to adapt the Chisel-generated signals into a parameterizable array of struct signals. Each wrapper is tailored for a specific configuration, one for 3 issues and another for 4 issues, and includes an interface that accurately corresponds to how Chisel translates a bundle into SystemVerilog ports. These wrapper modules instantiate the SystemVerilog interface module with the appropriate parameters and map the individual wires to the packed structures. In the end, the target SystemVerilog module is instantiated using the newly created interface module, ensuring a smooth integration and effective communication between the components. On the Chisel side, I created two black box modules for the two configurations, each selecting the corresponding wrapper files as its source. To finalize the integration, I incorporated a switch within the Chisel code to determine which of the two black box modules to use based on the issue size. This approach ensured seamless compatibility between the Chisel and the SystemVerilog components. To integrate an in-order vector pipeline into Boom, we initially considered using the Rocket Custom Coprocessor Interface, ROCC, as it appeared to be the most suitable option. However, upon further examination, we discovered that ROCC, its lack of support for direct L1 access, was a significant limitation that could not be overlooked. Faced with this constraint, we had no other option but to undertake the more complex task of modifying the core itself to accommodate the desired functionality. As shown in this diagram, the vector unit is encapsulated within an execution unit with a dedicated issue unit responsible for resolving any dependencies related to int or floating point operands. This execution unit is equipped with the ability to read and write data to and from int or floating point physical register files using exclusive ports. In addition to this configuration, we also implemented various updates to other components, such as the decoder and the CSR units, to accommodate the unique requirements of vector instruction decoding and the new set of control and status register that are introduced by the vector extension. Moreover, the vector unit establishes a direct interface with the load store unit to handle vector load and store requests, as well as their corresponding responses. In the case of a vector store instruction, the allocation process for one store queue entry occurs during the front-end stage, just as it would for scalar store operations. Subsequently, the vector unit patiently waits for this entry to become the commit head. Once the commit head is achieved, the vector unit reuses this particular store queue entry multiple times, effectively unloading all the store requests that originated from the initial vector store instruction. As for vector load instructions, the regular load queue entries are not allocated. Instead, a specific segment of a load queue entry is set aside and reserved solely for vector loads. The allocation of these reserved entries is managed by the vector unit itself, only occurring after a vector load instruction has been cracked and its associated address has been successfully resolved. Retrofitting the load store unit was the most challenging and time-consuming part of this project, mainly due to the existing mechanism being unsuitable for vector load store operations. In the worst-case scenario, a single instruction could require hundreds of load queue or store queue entries, not to mention the masked off or tail elements. The Boom core follows weak memory ordering, and the provided figure and table illustrate a survey of how dependency among vector or scalar, load or store are protected after the retrofitting. It's worth noting that the current design does not protect against the read after write hazard of a scalar store followed by a vector load. This issue could potentially be addressed by allowing a vector node to allocate a regular load queue entry in order to maintain a record of a dependent store mask. Our verification team developed a great tool to assist in verifying this design. The added debug harness is capable of collecting various architectural states and communicates with our bridge modules through a DPI interface. The checker then performs lockstep architectural checking against the instruction set simulator. It's worth mentioning that the instruction set simulator, named Whisper, was developed by my colleague, Joseph Rame, who presented earlier today. This tool has greatly contributed to the success of our project by providing reliable architectural checks throughout the verification process. Thank you for your attention, and I'm truly honored to have had the opportunity to share our work with you today. If you have any question or need clarification, please don't hesitate to file an issue on our GitHub page. We appreciate your interest and look forward to engaging with this community further.
Go ahead and thank the speaker. So I guess, are there any questions in the room for right now? Okay, first question, yeah, okay.
Hi, DJ, thanks for the talk.
Hey, Jerry.
I was just wondering, in what area of Boom did you find the most difficulty when integrating the vector unit, and like what kind of bugs did you find to be the most painful to debug?
Oh, it's always a load store.
All right.
Yeah, load store is actually a deal breaker because we found the way that we integrate the vector unit into the Boom, it's how to say, it creates so much issue, and we have to rethink about how to approach this in the future. And this is kind of like one of the lessons we learned from this project.
Hi. I'm not super up to date with the RISC-V ISA, but I guess there's vector extension planned, or like for the ISA itself.
That's what there is. Yeah.
Yes. Okay. So then my question is, have you then ran any programs with this vector extension, like compile them and ran them on the extended Boom core?
Oh, we did. So we run a suite of benchmarks. Some of them are using the intrinsics, and some of them are compiled with the LLVM, with the auto vectorization. And I don't have the slides right now, but if you are interested, you can look up the talk from my manager Srikanth. He talked in this RISC-V summit last year, and he presented the performance number we collected from this design.
Okay, I'll check them out. Thanks. And bonus question: which parts were generated with ChatGPT?
Oh, all of them. Yeah, it is a great tool. I couldn't really do this talk without it.
So you talked about some limitations of the vector pipeline with respect to it being integrated inside of the LSU, but if I remember correctly, it also didn't have some particular instructions implemented from the RVV spec. Is there any sort of timeline to get that fixed for your open source implementation, or fix any of the issues that you found with the load store unit?
This depends on how much time I can be given on this project. I need to consult with my manager, but in addition to the one I mentioned, there's another pretty obvious one that I may need some help from you guys, because you are more familiar on the Boom side, which is the support for exception. And I guess if we really want to make this working. We need to add a register renaming for the vector pipeline, and to some extent.
All right, thank you. Any other questions in the room? Okay, thanks so much.
Thank you.